Okay, so yesterday I talked about how to think about the area CFT from kind of, if it's going to work, how must it work? And then I said that states in gravity need to be related to states in the fluid theory, and then we solved scalar equations in gravity by doing some tricks for analytic calculations. And then we were able to match basically the idea that scalar operators in the field theory need to be related to scalar fields in the bulk, and then we said what was the relation between the dimension and the quadratic Casimir that followed from nice theory. Today we're going to talk about one conformity theory. We're going to talk about AdS in a particular version and CFT in a particular version. And then let me remind you that this is this very mysterious thing that quantum gravity can be equivalent to quantum field theory in few dimensions. And then the simplest original example is the one we all love, which is identical for Yang-Mills on, and now I'm being careful here because I'm going on the cylinder straight, is equivalent to type to be superstring on what's called global AdS5 process. Okay? So in the original paper from Mandelstam, this was R4, and this was Poincare slicing of AdS5 process 5. But we know better now. So this slight modification doesn't change this, but this is the good stuff to know. And here's the standard table. The isometries of AdS are the global symmetries of CFT. As I told you yesterday, global symmetries of the CFT need to be gauged, so correspond to a gauge field. So the isometries of AdS need to be gauged. But we know that because that's what we usually call a theory of gravity, it's a theory of gauged diffeomorphisms. So in particular, the isometries are a subgroup of diffeomorphisms. And if the diffeomorphisms are gauged, which is what we call a theory of gravity, then it must be true that the isometries are gauged. So these are not global symmetries in AdS, but they're kind of the part that survives at infinity. Okay. The radius of AdS to the fourth power is equal to a coupling constant on the other side, and this is Yang squared times n. On the gravity side, AdS5 crosses 5 has a dilaton, and that is unfixed by solving the equation of motion. So you're free to move it around, and that's the same thing as writing the radius of AdS in string units. So this is the radius of AdS in string units, and this is tooth coupling. If I use the radius of AdS in Planck units, I don't have the Yang squared times n, I just have n. So g Newton is 1 over n squared. It's not anything else. There's a flux threading the sphere, and then your quantization tells you that the flux needs to be an integer. That's what gets mapped to the fact that you have this discrete gauge group on the other side. This is additional data. This is not automatic, but the quantization condition on one side is related to something that is data in field theory on the other side. And you can think of this as being part of the solutions to the equation of motion, but it's a discrete thing, and then infinity is in some sense telling us that this is the right match. And then, as I said before, a state in gravity is to be a state in the CFT, and one particle state in gravity was matched to one particle in the sense of single trace on the CFT. Okay. Now there's a little bit of how do we write the field content of when I go for Yang-Mills. So I'm going to use my favorite notation, which is there's a field Z, and Z bar, and phi I from I to 4. These things together form a 6 of SO6, which is the R-symmetry group of equal for Yang-Mills, and that's the isometry of the S5. And then Z is the highest weight state of SO6 in the 6 representation, and that's what I call Z. Z bar is the complex conjugate of it. It's the most negative weight. And then phi 1 through 4 can be obtained from Z by rotations. Okay, and then there's the gauge field mu. And then there's spinors. There's left-handed via spinors and right-handed via spinors. And one of them transforms into 4, and the other one transforms into 4 bar of SU4, which is equivalent to SO6. So that's in the spinor representation of SO6. So we're not going to use them, but they kind of are floating around as part of the definition of this theory. And then bosons have dimension 1, and fermions have dimension 3.5. That's the free field counting. And they're all in the adjoint of SUN, so I've kind of skipped all the SUN indices. So we need to keep track of these extra indices. Okay. A single particle state needs to be a single trace. This is the large N understanding, factorization, that says that if you're doing things at large N, there should be large N factorization, and then single traces correspond to essentially free particles. And then that's what we do. And then a BPS particle, you can think of it as the thing that maximizes the R charge given the dimension, or that minimizes the dimension given the R charge. So the point is that if you want to maximize the R charge, you take the highest weight state of SO6 and you just take it as many times as you need. And then trace of Z to the N is the guy that has maximum SO6 R charge given the dimension, or rather that has minimal dimension given the SO6 R charge. So we're just maximizing the weight. You just take a highest weight state. These turn out to be BPS automatically. And this starts at N equal to 2 or higher. This is the difference between UN versus SUN. And for a lot of things, it's actually SUN is the right one. So this is the highest weight state of an SO6 representation. This is the symmetric traceless representation. And then it has a lot of null descendants. So that's what BPS means, but this has BPS, so it actually has a lot of null descendants. So it has to be massless in 10 dimensions. And then there's some special properties of these states which have to do with very special details of the N equal 4 superalgebra. Is that even if you include perturbations and you go away from free field theory, these states can be lifted because it does not allow an anomalous dimension. And the reason for that is that if you were to try to build an anomalous dimension, this representation would need to get their extra polarizations from another representation to kind of join it together and to take it away from having all the null states vanishing. And if you look at what that representation means, that has a negative norm state. So that basically forbids that from happening. So these states actually survive from weak coupling to strong coupling. The usual story is that these guys are in the chiral ring, so okay, so they're protected by supersymmetry, but but here's something nice, and that's that because you start at N equal to 2, the minimal spin for this guy on the sphere is 2. And what that means is that this is the spin of the particle in 10 dimensions is 2. So this is part of the gravity multiplet. So this is where you see that this is the gravity multiplet. And spin and SO6 numbers are quantized. If you look at the table of supergravity and you do it in this way of classifying states, you see that that's exactly what you get. Although the way it was written in the original papers was computing the mass spectrum and then converting dimensions to masses requires kind of complicated change of values, also known as turning these deltas and computing, finding the relation to mass. And then people had these masses, both some square roots and some random numbers, but they really follow just from the fact that the SO6 is compact and that you have a highest weight state of that's BPS, that's kind of has massless descendants. Okay. So these are single particle states, and if you have these guys, it turns out that you have all of the possible partial waves on AdS 5 crosses 5. And one of the reasons, which is something special about AdS 5 crosses 5, is that all the null geodesics are conjugate to each other by the conformal group. So if you have one, you can always rotate it to any other. So in the semi-classical limit, that shows you that any one of these particles in their multiplet, you can get to any other particle. And the only thing that survives is the quantization of the spin on the circle on the sphere. Okay? So what that means is what's the momentum on the sphere, that's the invariant of that, the p squared on the sphere, and that's what n captures. Okay. So these are the BPS states, and then you say, okay, how do we get non-BPS states that are single particle states? So we expect this to be dual type to be string theory, rather than just supergravity. If you do these guys and take and just start with these, this provides for you the complete one-particle states of supergravity for a full 10-dimensional theory. So you could be done with this if you're just doing supergravity. But we know that this is not the complete spectrum of the theory. We know there's more operators that are single trace. And one way to understand how they work is that it's very convenient to expand near a BPS state, meaning you take a trace of something that has a lot of z's and very few other stuff. And this is a good starting point to try to understand what planar diagrams and non-planar diagrams are doing. So you can think of these as defects moving in a sea of z. And then you just have to go and compute anomalous dimensions. So you can compute them perturbatively, so you can do perturbation theory. And the gap, meaning the lowest normal dimension, scales as powers of 1 over j, and there's the tooth coupling showing up in there.
So here you're supposing j large.
I'm supposing j large, yeah. So it's convenient to start this way. So if you include the interaction term plus planarity, there's this kind of commutator that shows up. That's the scalar thing. And that lets you take one of these defects and hop it past one of the C's. But if you try to do multiple hoppings, you find that you're jumping over lines and that's non-planar, and then those things are... So it's a nearest neighbor stuff. And then there's only 4 of these guys that you have around. So you can think of these as defects that can hop between the Z's, so it's nearest neighbor hopping. So the point is that because it's kind of finite number of states here, at least if you start with I's, then you can think of these as mapping into a spin chain, and then what you have to have is a Hilbert space on a site, and then how you hop around. So this is something that in condensed matter theory you would do regularly. And then you just start with this, and then you can try to go a way of saying, okay, there's some sort of spin chain relabeling of this stuff, which if I have a lot of Z's, this can look like a spin chain. And then writing the Hamiltonians to various orders, perturbation theory is nearest neighbor next to nearest neighbor, and some more complicated stuff as time as well. Okay, so you can call this the spin chain program. So we can do this on any theory. You can kind of do a spin chain program. There's nothing special about doing that from this point of view. If there's some preferred Z that you have around, and that you can show that there's some symmetry that protects the number of Z's or something like that, and that lets you hop around other things, you're going to get a spin chain. So you can just start writing random spin chain Hamiltonians. But this is the stuff that we were doing in 2002, famous BMN paper. It was basically stuff like that. It was the simplest approximation where we just didn't consider any scattering of the defects. And then Minahan and Zarembo wrote this paper in 2002, a little bit later, where they showed that you could actually do a variance as to one loop. So here's a fact that I didn't know when I was writing the first paper. Otherwise, I would have written this paper also. And that is that if you take a nearest neighbor SU2 spin chain, it is unique and it is integrable. An SU2 invariant spin chain. And that's called the IC model, right? Not the IC model, but the
XX.
the XXX model. So it's completely solvable. But if you do it with SO6, you take the 6 tensor to 6, that's the possible list of intermediate states, you actually get 3 non-trivial representations of SO6. There's the trace, and then there's the symmetric and the antisymmetric. Okay? Symmetric, traceless, and antisymmetric. The fact that there's 3 representations means that it's not automatically integrable and you have to check something. And this is what these guys did, and they showed that this was soluble, that it was soluble by Bethe ansatz, and that it was exactly an SO6 integrable model. And this was not expected. Okay, so this was very new in that sense. And then Beiser and Staudacher said, okay, what other things can we have? And you can have derivatives of all of these things. And then when you count derivatives, a derivative acting on the field, that gives you the SO2 representation. So you go, instead of the SO6, you go to the SO2, 4 theory of descendants. And then what you get is a tower of states, an infinite tower. And you can organize them like SL2 representations. They look like an infinite tower of SL2 representations. And if you use all the Lipetov SL2 anomalous dimensions that were computed for QCD many, many years before, you find that this is also an integrable spin chain. And this is what people call the XXX minus a half model. So it's basically an analytic continuation of XXX to having infinite spin representations. And if you put these two together, you get that the full structure is integrable to one loop order. Okay? So this gave rise to what's called integrability program for strings in AdS 5 crosses 5. There's a great review of that, which is 400 pages long and about 400 authors. I mean, not really, but it's about 20 authors. But it's kind of divided into like 8 sections, and each one of the sections was written by different people. And every time you want to read something about what was known about this stuff up to 2012 or 2011, when it was written, everything is in there, and then that's the place to actually start understanding this program if you want to do so. It's nasty in the sense that you really need to know a lot of integrability and various other things, and it takes a couple months or years to actually absorb this stuff. There is an interpolation between weak and strong coupling. As far as I know, this was solved in terms of a Y system. So Kazakov, I think, wrote a Y system that purportedly solves the theory. Don't ask me what a Y system is, I just know the words. It's another way of writing beta ansatz solutions with some other ingredients that you reconstruct the stuff, okay? And this takes care of finite size values rather than the infinite spin chain. But integrability as a thing is not really proved. You can think of it as a working assumption. So what people do is they take this working assumption and then they make predictions for various loop orders of some anomalous dimension of some operators. And then other people who know how to do these things with computers go and do 5 or 6 loop order computations in n equal 4 Yang-Mills on a computer. And they resum these things. And then the anomalous dimension is written in terms of factors of pi and numbers and you square it times n. And that's the same thing you get from doing diagrams. And then people compute these things numerically or whatnot, and they find a match, as I said, up to 5 or 6 loop order. So people have gotten really good at getting this far. So the idea is that we believe it's true, and then if it's true, then we've solved it, then we can move on. So we understand the spectrum of strings on AdS 5 crosses 5 in the sense that it's solved by some complicated Y system beta ansatz, and then solutions in terms of beta ansatz are not solutions in the usual sense, they're implicit, and if you actually want to get the numbers, it's a huge amount of work. Okay.
And all this just in the planar limit.
Yes, this is just planar limits. Okay.
I think the loop order can be higher for some very specific think of C.
This is why 5 or 6. Yeah. I don't know where the number is at this
I think
moment.
it can be even 8 or so.
I don't know that people have done the 8.
Kind of operators.
For the Konishi, right?
Yeah, like.
But I thought it was stopped at 6, the one that they did numerically. I thought. I'm out of the 8. I mean, this is, last I remember it was 5 or 6 loops. And then they get better at it, and then they might, I mean, combinatorics of these things grow quickly. So the question is, how well do you control the combinatorics on a computer to actually write the answer? Okay, very good. So if you just look at what type of energies you cover energies up to order square root of n. So square root of n is basically a string stretching from one side of the S5 to the other one. That's square root of g Yang-Mills squared times n. So you just kind of unpack that a little bit, and you have order square root of n. So the idea is that when you're up to order square root of n, actually less than this, you're in the string regime, and you can basically say you have a theory of more or less free strings, and then you have to divide your energy between the strings. And yes, there will be non-planar corrections, but from the point of view of single particle states, we have some understanding of what you get. And that's enough to produce some non-trivial results. Okay, so if you do string theory, you say, okay, what do I know about string theory? It has strings, okay, and then you ask, okay, well, that's kind of the perturbative spectrum. And what's the non-perturbative spectrum like? Well, there should be Dbranes. So are there Dbranes in the theory? So the next step up is the first non-perturbative object that one can write down is to say, okay, are there Dbranes in n equal 4 Yang-Mills? And the answer is yes. So it turns out that there exist half BPS states that are Dbrane-like, extended objects. Okay? They're called giant gravitons. So the point is that half BPS states are gravitons, and these are extended objects that have the same quantum numbers, so what better name than giant gravitons? And then people found another solution, and then they call those dual giant gravitons. I hate this dual name, but this is the way it's done. So the original paper that found the giant gravitons was McGreevy, Susskind, and Tombas. I'll give you a very simple description of these guys. And then the dual giants were discovered simultaneously by this paper, who tried to call them Goliath, and that didn't stick. And then dual giants was what these guys called it, and that kind of stuck. I don't know, Goliath sounded a bit better. But it didn't stick. Okay, so giants and dual giants. Okay.
Sorry, so the statement is that you know that in the string theory, apart from strings, there should be Dbranes?
Yes.
So the idea CFT duality tells you that there should be something in n equals 4, and that something are these giant gravitons. Is that the statement?
The point is that these giant gravitons actually are supersymmetric. So you can find them in
Yeah.
link coupling. They're protected by supersymmetry.
But are they gauge theory objects,
Yes.
or are they string theory objects?
Well, they're both. As Dbranes, they're string theory objects.
Yes.
And they correspond to some single particle state, or sorry, some operator
Right.
in the dual field theory. And then for a long time, there was a question as to what this was. Okay, and it was not clear what it was. Yes?
So where does the half in the BPA states come from? You say half of the solutions, but which half?
So the usual story with the Dbranes is that they preserve half of the supersymmetries. So that means that usually in the superstring you have left-moving supersymmetries and right-moving supersymmetries, and then the left gets mapped into the right at the boundary, and that means that only half of them are preserved. So if you're lucky, you have objects that preserve half the supersymmetries, and it turns out that they're Dbranes in this case, and then that's that. Let me give you the description of these objects. So if I say that they're Dbranes, that means that they have 3 space and 1 time direction. And then if you say that they're happy pairs, they have to have a particular set of quantum numbers, they have to be invariant under some rotations. So we know what these objects are, but there's a simple way to write them, which is I take the phi sphere and I write it in my favorite representation, which is z bar plus sum of yi squared equal to 1. Why? Because this is a 6 of SO6. So I'm using a representation of the sphere, which uses my decomposition that I want. So you consider a 3 sphere that's fixed at some value of z. If you know z, you know z bar. So you take care of this one, and then you can solve for what the size of this 3 sphere is. It's a unique 3 sphere, and it's on some point on the z bar, on the z coordinate labeling. And then all you need is that z of t is z0 exponential to the it, and this is actually the solution. So these objects move around. They move around at velocity 1. You can write z as cosine theta exponential to the I phi. So the equation motion is that phi dot is equal to 1. Okay. This is the description of the giant gravitons. And this sits at the origin of global AdS coordinates rho equal to 0. Okay. So this is the giant gravitons. How do you find the dual giants? So we do a dual analytic continuation. You write AdS 5 as xi bar minus the sum of y squared equals minus 1. This is the way I was writing. Sorry. This still should be equal to plus 1. And then the idea is you use xi is equal to cosh rho exponential to the it. Okay? And this sits at the origin in the z coordinate, so I have the z coordinate on the other side, so that's called theta equal to 0. And again, the equation motion is phi dot equal to 1. So this can be obtained basically by proper analytic continuation of stuff. This should be a plus 1. In any case, so we're good. They're BPS, so the R charge is equal to the energy. And for giants, the energy is n times 1 minus z squared, which you can write as n times 1 minus cosine squared theta. And for the dual giants, you change the sign to a plus sign, this to a minus 1. And then you get c squared minus 1, and that's cosh squared rho minus 1. And then what happens is that you do this thing and you find that it is the same and it's obtained from the other bianalytic configuration. Okay, so it's a nice way to put them together and to realize that the objects are very similar.
Sorry, so a better name, I guess, is like sphere giants and AdS giants. So
Yes.
fine.
But that's not the convention in the literature. Just giants and dual giants. I hate this stuff.
Yeah, I can see why.
But AdS giants and sphere giants are better. Because they're not really dual, they're not dual in any sense. Okay. So just look at this stuff and you say, okay, the giant graviton, what's the minimum values you can take is 0, so the maximum value V I can have is n. Here there's no bound, but you could say rho is order 1. Then you say that its energy is up to order O of n. So that's great. So
Will you tell us how the real duals of these things look like in
Yes.
n equals 4? Thank you.
yes. So the point is, if you take multi-traces, although BPS, they're not orthogonal at finite n. So it turns out that if you want to understand physics, you have to do what Antal and Sanjay and Morley did, which is, let's find an orthogonal basis to describe the finite n physics, and then the question is, what is that? Because we need to go all the way to order n. So finite n, we're going to hit that limit, but we cannot just ignore it. So how do these dual operators fit? So let me give you a trick on how to think about this, which is that if you start in free field theory, there's upper indices and lower indices, and you're going to have some set of z's, and you're going to have some upper indices and some lower indices. But in the free theory, it has a symmetry of upper and lower indices, which is SUN up cross SUN down. Actually, they all have the same mass, so you actually can rotate these things into one another. In principle, you have a higher symmetry than just SUN. So what you can do is decompose the upper indices into SUN up representations. And this is a tensor with n indices, so the way you do that is you just pick a Young tableau.
So these indices are in the fundamental of SUN.
These are in the fundamental of SUN, so you get some Young tableau. And the point is that different Young tableau correspond to different representations, and they're automatically orthogonal with respect to the SUN up indices. Now what happens is that this needs to be SUN invariant under a diagonal embedding of some SUN inside this product group. But that doesn't kill the statement. So what you do is you basically take the appropriate invariant, but the structure of the tableau of the upper indices stays fixed, and they're automatically orthogonal even after you average over the diagonal group on the states. Okay? So if you decompose these things, again you get a Young diagram for upper and lower indices. They need to be the same Young diagram. And this is what's called the sure polynomial basis. And then there's a unique gauge invariant built from this data from each one of these Young tableau. And then the proof of orthogonality, the original one, was not like this. The proof of orthogonality was basically by direct computation of the inner product of these things and showing that different representations were orthogonal. The advantage of doing that brute force calculation is that you also get the norm of the state and not just, how do you call it, a statement that it's an orthogonal basis. You actually get something more. Right. So how they match is, this is 2001. Here's 2001 earlier. This is Lauser-Vanenian, Berkus, Nachmi, and Strasler. They said, okay, traces are not good, so they said subdeterminants are good. They're one column Young tableau. And they said these are giant gravitons, and then because the columns end at finite n, they have a maximum angular momentum, which is n, which is the number of boxes that you can have in your tableau. And they said this is the way it should work. And then they said, okay, this is it. And then Collinger became a Google and said, well, the dual giants are the one row states. Right? So rows and columns are more or less showing up in the same way. Okay, but we still haven't proved that they're Dbranes, right? So the thing is that just by saying these, we have some evidence that they are Dbranes in the sense that for one of these, you get a bound on the angular momentum, and for the rows, they can extend all the way to infinity. So from the point of view of the dual giants, their energy could go to infinity, so that much is matched. But you need to be able to do more. So if you have Dbranes, you have to be able to attach strings to them. So this was basically...
But the fact that they are BPS is more or less clear.
Yeah, the fact that they're BPS is that they're built just out of Z. Anything built just out of Z, if it's gauge invariant, it's at BPS, and you cannot lift it, so all of these guys are protected by supersymmetry. There was a controversy at the beginning where people hadn't realized this statement about the negative norm state in trying to lift these states up. So people thought that there was some tunneling between the giants and the dual giants, and there was a whole kind of, how would I say this, fog of war, you can say, or some, complicated dust. And when the dust cleared, it turned out all of these states survive, and there was no tunneling between them. They're all orthogonal, and they're all representations that survive the large n limit, not the large n limit, but the strong coupling limit, unimpeded and supersymmetric, and they all live all the way to coupling. Okay. So what we did with Balanced Riemannian, Feng and Huang was said, okay, the way you attach open strings to these things is you take an open spin chain rather than a closed spin chain, which was the way we started with the closed strings. And you have some dangling ends. So a dangling end is an upper index and a lower index. Then the question is, what do you do with these indices? Well, you have to somehow attach them to whatever you have here, so you have to symmetrize or anti-symmetrize with respect to the indices that you already have in the giant. And then we said, okay, you add these objects, and you intertwine the indices in the only way which is allowed by diagrammatics. And then we said, okay, this is the way you attach these things. And then 10 years of toiling. So Robert and Rudam and company basically constructed a proper orthogonal basis of these things that come. And they did this systematically as opposed to the way we did it, which was just attach one string and see what happens. They actually taught us how to more or less really build this stuff more systematically. And it is a combinatorial tour de force. This is the only way to describe it. So this is constructing the restrictor basis and learning how to count states and compute, and computing one loop anomalous dimensions in terms of all this data, and giving us tables of this stuff. And then I was kind of trying to get around that and not do the work. But I was trying to understand the boundary conditions on these spin chains. So what is the boundary condition that you get? And how do you solve it? And then I was trying to get around some of these things by doing some theory of collective coordinates and solving for the ground state and doing some of the stuff. And so what does it look like? And the point is that combinatorics doesn't automatically tell you what's the correct wave function to start with. This other stuff was kind of the cheat sheet to go to the right basis for these computations. And then, as I said, they're Dbranes, you can attach strings. Dbranes have a gauge symmetry on the world volume, so you have to have as many strings coming in and out. That's reflected in the fact that you have to have a Young tableau for upper indices and for lower indices, and however many boxes you added in the upper indices need to show up in the lower indices as well. Okay, so the Gauss's law is basically strings in equals strings out, and that comes out automatically. And then the mass of the string should roughly be a distance. That depends on the geometric position of the branes. And what happens is that when you start with the giant gravitons that are combinatorial determinants and superdeterminants and various stuff like that, these are objects that have a fixed angular momentum, so they have to be delocalized in the dual geometric variable. Whereas what you want is things with relative angle being fixed. So that's why collective coordinate was necessary. Okay. So the idea is that there's a formula for this. I'm going to do a little detour now. So I'm going to tell you what other ingredient is required to understand the mass formula. And that is that if you consider bigger sectors without supersymmetry, or it should be without supersymmetry, it turns out that on the spin chain, there's a central charge that appeared from the work of Weiser. And in the infinite chain, it can be understood as sending y to y commutator z. So that doesn't change the length of the spin chain if the spin chain is infinite, but that relates the states, and then the object that does this is the thing that kind of controls the dynamics of the spin chain, and this actually survives to all orders in perturbation theory. And when you compute the QQ commutator on the worldsheet of the spin chain, you get that this is proportional to the exponential to the I times the momentum, and this is evaluated on a single magnon. Okay, so there's a long story here. The point is that this thing over here produces a dispersion relation which has this sine squared of p over 2, which is the contribution from the central charge. And then the magnons that are appearing in the fundamental magnons that are appearing in the spin chain description actually are short representations of the supersymmetry, so they saturate this BPS band, which is of this form. Okay? And this is good to all orders, and the function h of lambda is lambda. Okay. This is very non-trivial stuff. And this is the strong tooth coupling constant. So the point is that when you take the closed string spin chain, go to infinite size, the central charge shows up here and provides a dispersion formula for you, and this resums everything to all orders in perturbation theory. Right? This is an anomalous dimension with an expansion in the tooth coupling that has all powers of lambda. So this is a resummation.
Sorry, why strong? I thought this was true for all values of the tooth coupling.
Yeah, but the point is that if lambda is big, then you cannot expand this. You're beyond the radius of convergence of the square root of expansion.
I see. So for large lambda, you wouldn't expect like a square root of lambda times sine of p.
Yeah. So for large lambda, you expect square root of lambda times sine of p. Right?
Yeah.
If you get 1, you get square root of lambda times sine.
Good. And for weak, you say that it doesn't start with a 1 for a small lambda.
No, so for small lambda, it starts with a 1.
Yes.
Because the defect carries a value of delta minus j, which starts as 1. This is the field theory value, plus.
Maybe it's a stupid question. So isn't this formula valid for all values of lambda?
Absolutely.
Ah, great. So yeah, so I didn't understand why down we write strong.
So when you're going to compare two strings,
Right.
you have to go to lambda large. Okay.
But there was another question.
Yes.
What do you mean by saturate the bound? I think I missed that.
The what? The saturating band?
Just the term, yeah.
So the representation theory of the PSU2 2/4 centrally extended spin chain stuff, the stuff that survives as a PSU2/2 squared symmetry, okay? And then saturating the BPS band in that case means that in the representation theory, there's short representations. And the short representations are annihilated by some of the supercharges. Okay, and then when you saturate the band, that means that you're in a short representation. And then for those short representations, this is the dispersion relation, which follows from it being annihilated by some of the supersymmetries. So it's like a typical BPS argument. I mean, it's a nasty formula because there's the square root and all this other stuff. Okay, this is the miracle of this stuff. But it turns out that if you go to finite p, this is the dispersion relation of something that's called a giant magnon. Okay, so I introduce the word giant again. So what you do is you take a magnon and you go to a p finite rather than infinitesimal, and then that p finite corresponds to a finite angle on the z-plane, and it goes from one side here to the other one, and then there's a string stretching from one side to the other one, and then the string that stretches from here to here. The classical solution to that is called the Hoffman-Mandelstam giant magnon. Okay, and then when you try to understand the string, it looks like a polygon of these objects that kind of crisscrosses around, and this is a description of the physics. And this with a lot of z's, so this is the far away physics, and then when they get close to each other, stuff happens, and this is what we saw yesterday in the talk by Jacob and Zild. When things get close to each other, they kind of bend and do something for a little while, and then they scatter. Okay. And then, again, this is in the same splitting as before. We have S3 over S5 and a disk, and the disk is this z coordinate. So they go in a straight line, and they sit at a point in S3. Okay. So now if you do the same thing for these open strings, what you have to do is you have to cut them at some finite value where you insert your favorite giant gravitons. And then the final answer after adding some angular momentum and some other stuff is that delta minus j is some square root of these objects like this. And this square root formula is the same as before. A single magnum is j2 equals 1 in some sense. This is a bound state of these objects. These bound states carry R charge in the SO4, which is equal to J2, and this is what you think of moving on the giant graviton at some finite amount of momentum. And if you look at this looks like a relativistic dispersion relation where it's p squared plus m squared, and this m squared is this kind of thing over here. And the m squared does look like a distance because it's the difference in position between the two Dbranes in some form, so it gets that intuition right. How did we prove these? Because we realized that these objects had to be in short representations of supersymmetry, although the original calculation was do the 1 loop, do the 2 loop, do the 3 loop, and we started seeing square root formula start to show up. And then the idea is that these giant magnons form bound states, and they're called Dirac giant magnons. And then you have to find the corresponding sigma model description of these guys. So in the gravity side, you do it by there's papers by Kalusius, Bradlin, and Volovich, where they computed a solution of the sigma model by inverse scattering method that had the right quantum numbers and that produced the correct dispersion relation. Okay, so you have to put all these things together, cut these things in the right place, evaluate the stuff in the sigma model, and you get this expression. But if you just plug in what the value of the central charge is C minus C tilde, and this is actually a geometric answer for what the central charge is. Okay? Very good. So it turns out that the Dbranes have sourced the central charge of Poisson. So if you remember what happens when you have two Dbranes that are separated from each other, they've also sourced the central charge. So when you dimension reduce to the appropriate dimension of the Dbranes, you get central charges, and the distance between the Dbranes is the central charge, and it's something that you source by the Dbranes on the string. So the extension of the string produces a non-trivial central charge on the string, and you still have short multiplets. So n equal 4 Yang-Mills, even when you go to the Coulomb branch, the massive particles are still in short multiplets of the supersymmetry, and that means that you've generated a central charge. Okay? And the idea is that this is the same physics. And this is what usually we call the Higgs mechanism for separating Dbranes and producing masses. Okay, so all of this stuff is to show you that after the dust settled, so from 2002 to 2014, okay, 12 years of various groups doing stuff, eventually we converged to a number, and the number was there's a dispersion relation for these objects, and the dispersion relation is a simple answer. And if we had known what we were doing from the beginning, we would have guessed a lot more quickly what was going on. But it took years of computations before we got there. Okay. Okay, so what's the next step? The next step is, so we are at order n Dbranes plus order square root of n strings between Dbranes. And then you would say, okay, let's keep on going up. So what's the next dimension that's interesting? It's going to be n squared. Okay, why? Because that's when we're exploring all the degrees of freedom of the matrix, and then you can expect different things to happen. So here's the question. Can one solve the most general half BPS state in gravity? So if you start just with Zs, you say, okay, I have these young tableaux, there's going to be some big ones. Those have a gravity interpretation. Right?
Sorry, before you get ahead, can I ask you a question? So I have, just for the states of order square root of n or less, I have an intuitive understanding of how much half BPS states compared to all states.
Yes.
So what about order n and order n squared? So we are looking for half BPS, but how small are those compared to the total?
Oh, they're tiny. The entropy is of order n, and the entropy of all states is of order n squared.
I see. But also for n squared, also for the geometries.
So yeah, black holes have entropy of order n squared, and these things have entropy of at most order n. because Young tableau are really related to eigenvalues. Okay, and eigenvalues, there's only an eigenvalue, so the entropy goes like n. So n versus n squared, nothing.
Thank you.
Okay. Okay. So so now I'm going to go to another interpretation of this stuff, which is you can think of this as a matrix model for a single matrix Z. Okay. And you're doing gauge invariant matrix model, so you're going to the singlet sector of the matrix model. Yes, you have invariant part. And then the idea is that there should be a free fermion description, and then from what we know about free fermions, the Schurs are actually Slater determinants of some free fermions in the way. Okay, so there should be a free fermion description. And one of the questions you can ask is, what's the ideal free fermion description of these guys? It turns out that the ideal free fermion description is in phase space and not just on a line. Okay, so if you do things in phase space, you have x and p, and each fermion occupies an h bar unit of area. And then a wave function of the fermions is basically you put fermions and then you don't allow them to overlap. So you have occupied regions and empty regions, and then you describe that in this phase space by some sort of the position of the corresponding fermions. Okay, that's the description. And these are free fermions in phase space. This problem shows up all over physics. It's also known as the lowest Landau level physics because an electron in the lowest Landau level, the position in X and the position in Y, properly reduced, do not commute and have a non-trivial structure. That gives you a non-trivial phase space. So it turns out that this is the same physics as quantum Hall droplets. So for you who care about quantum Hall droplets, this is what's going on. And you know, this was something I wrote in 2004. And then the reason that I wrote this paper is because I was trying to understand the paper of Corley, Gravitons, and Woodham, and tried to figure out what was going on in a way that I could understand it rather than just combinatorics. Okay? I think they knew this stuff. I just made pretty pictures. So in these representations, you think of traces as edge states and single quanta with fixed momentum on the circle of the edge. Whereas dual giants and giants are fermions and holes removed from the droplet respectively. So there's a sense in which fermions are just the rows of the diagram, and then dual fermions or holes are the columns. So if there's no distinction between fermions and holes, they have a description on both sides, but a hole can only kind of go all the way to the center of the disk and then cannot add more energy there. Okay, so this suggests that the most general classical limit that you can have of these fermions on the plane is by basically zooming out and getting regions that are fully occupied and regions that are empty, and then these are called incompressible droplets on a 2D plane. And it turns out that this is a very non-trivial statement. This is actually exactly realized in gravity. This picture of free fermions droplets of coloring of the plane of empty and full regions is the solution of all the smooth solutions of supergravity that show. And this is what's called the LLM geometries, which we also saw yesterday, but I like to write them in a different form. So there's a time direction, okay? There's a y direction on a 2-plane, the xi are 2-plane. There's 2 3-spheres, so BPS states preserve an SO4 cross SO4 symmetry, and that's realized by isometries here. And then you ask that these things basically are annihilated by supersymmetries of the right type. So what that means is that there's killing spinor equations, and then you use killing spinor equations and supergravity techniques. So you sandwich these killing spinors with one another with gamma matrices, and you crunch and crunch and crunch and crunch, and you get conserved vectors, and there's a one form that's conserved, the one form that's exact defines a variable y, dy is the one form, and that specifies that the y variable is special. Then you solve more stuff, you plug it in, and you get this thing. This is a paper of 2004. Okay, it's a mouthful in the sense that it's a hard computation. Okay, but here's what's important. if y goes to 0 and z is different than 1/2 or -1/2, then the radius of this sphere and the radius of this sphere both go simultaneously to 0, and then you get a conical singularity. So what needs to happen is that as y goes to 0, one of these two prefactors needs to get a pole or needs to blow up. So either z is equal to 1/2, and then this one blows up and cancels the y and gives you a finite radius, or z is equal to -1/2, and then this one blows up and cancels the y. So one of the radii can shrink to 0, and then you get a standard conical representation of flat space in polar coordinates. So you get a non-singular solution. But it's important that z is equal to +1/2 or -1/2 exactly when y goes to 0, which is the degeneration limit of the spheres.
So this is y of that. So I don't understand. So is the red is.
I'll be more careful about what z is, because z is not one of these coordinates. Z is a function. So there's also attendant fluxes, so you can construct the solution in z. And z is something that's a function of x and y that satisfies a linear PDE. So a linear PDE, elliptic, if you give the boundary conditions, there's a unique solution, and by the maximum principle, if z is +1/2 or -1/2 on the edge, it's less than 1/2 or -1/2 on the interior. And if you look back at this thing, being in between 1/2 and -1/2 is required for this thing to be real. So it's a good solution, this works well. And then you can see that this is a proper metric with proper signature that doesn't blow out. Okay. So reality of the metric just requires that z is less than 1/2, and then non-singularity requires that z takes the value +1/2 or -1/2 on the boundary. And then there's this point where that +1/2 goes to -1/2, and you need to analyze that joining a little bit more carefully, and it turns out that there you're joining them on a plane wave, so it's a weird coordinate system for this stuff, but it works. Okay. So the absence of conical singularities really forces this stuff, and this provides a two-covering of the plane, and then these are all the horizon-free smooth 10D geometries that you can write down. Okay, and this is what a typical LLM geometry is. Okay, and then it turns out that this is a non-trivial statement: is that the topology of the picture encodes the topology of spacetime. So if I change the number of cycles, I change the topology of spacetime, and this is why they're called bubbling geometries, because you have non-trivial bubbling cycles, and the way you build that cycle is that a sphere goes to 0 size on the red part, on the plane, so you can thread that sphere around that thing, it has gone to 0 size, and then you put a dome around it, and then when you dome, it has finite value. So this is a representation of a disk with a 3-sphere, where the 3-sphere vanishes at the edge, so it's a 5-sphere. That's a way to write a 5-sphere, so this is a non-contractible 5-sphere. Why? Because when you try to push it here, that size is finite, so you cannot move it. You cannot move it without breaking. Okay. They have conserved area, so the area is quantized, and the area of each one of these droplets is quantized. And that's what gets translated to fermions having integer area. And it's a very non-trivial statement. This didn't have to work at all. I worked on these things on free field theory. They worked on them in supergravity, and it turns out that the description is absolutely the same. They have a conserved flux, so n is the integral of the density, where the density is the red area. Plane. And they also have an energy function, which is rho of x squared dx squared minus the energy of the Berenstein. Okay. And what's amazing is that this is actually a complete classification of all the smooth supergravity solutions that are asymptotic to radius of 5 cosine squared. Okay. What's the energy of these objects? They're of order n squared. This is just something that comes out.
The fact that the entropy grows like n is because the area is quantized, and you can understand how many of these things you can have.
So eventually you get free particles moving around, and there's only n particles. So the entropy has to be of order n.
Right. So it's 2 to the n, and the log of that is n.
Yes.
Good.
Yeah, I'm good. I'm almost done. Okay. So this is all the stuff that, in some sense, starts from half PPS and moves all the way up, and small things around half PPS. Okay. So this is a particular story of some of the things we know. And I've just been kind of cranking up the dimension as I go along. And then this is roughly where we are at. So if you think of it as the AdS CFT dictionary, is we know very well the AdS CFT dictionary of one letter. So, okay. We know more or less well the dictionary with one letter, a lot of them, a few other letters. So you can think of those as the short words. So I know how to say hi, bye. But then there's the problem of what happens to all the other states, which are more typical. So beyond, what else have people done? Okay, same energies but no BPS, so energies of order n squared. This is what we call black hole physics. Okay, and we're stuck there. We really don't know how to do that. I mean, we know the specific heat, but this stuff is complicated. These states are actually renormalized from weak to strong coupling. The spectrum goes from being discrete integers to being essentially continuous. And we have very little clue on how to deal with these objects. And we want to solve the quantum information paradox of the black holes. We need to start dealing with these guys. And a lot of people are trying, but we don't really know what's going on. What we know about these things is that they correspond to terminal field theory at high temperature. Okay? Very little is known other than the specific heat or the equation of state. I mean, that's something. We know something about the equation of state. In gravity side, we know what that is. It's black holes in AdS. There's tons of papers on that. Gibbons Hawking and various other things like that. Okay, so the specific heat of the free field theory is of the correct order of magnitude to compare to the specific heat of the black hole. There's a famous 3/4 difference between one side and the other one, and nobody has explained that yet. So we don't know that stuff all that well. We know that it's kind of ballpark, okay? And then you can ask, well, what's other stuff that people have done? So there's a whole other set of results, which is in a different expansion around different BPS objects. So there's Wilson loops. There's some Wilson loops that are supersymmetric, and you can compute their expectation values by localization. And these different kinds of matrix models. And then the number of people involved in these is a huge number, and they're pretty orthogonal to the list of people that I gave you there. Okay, so people who do localization are not the same people who do integrability, and they're not the same people who've been doing these Schur polynomials and stuff. The other stuff that came up from n equal 4 Young Mills was these helicity methods and this integrability on the S matrix. It's very clear that the integrability of the S matrix, the way people write it, is related to the integrability of the spin chain of anomalous dimensions. My feeling right now is that this is like going from the continuous representation where you diagonalize one thing in SL2 and you go to a different representation where you diagonalize momentum rather than. Okay, that's a nasty Fourier transform, because to go from discrete to continuous representation. But presumably there's some relation there that shows that it's really the same structure. It's the same integrable, it's the same group theory on both sides. They're both integrable, so cannot be very much, but what people use there is this Yangian symmetry, and then they use this stuff to say all kinds of fancy things about scattering amplitudes. And as I told you yesterday, the scattering amplitudes are a little bit of a weird thing because they're not really infrared safe, they're UV safe. So what people think about this stuff is this S matrix in the UV safe sense, and then you would have to dress it up with junk in the infrared to make it proper. Okay. Now I talked everything about n equal 4, but there's all the CFTs that people have done. There's ABJM, there's Gravitons-Strassler, there's a ton of candidate duals of field theories which are non-trivial on the field theory side, being dual to things that are non-trivial on the gravity side with some non-trivial topology, something more like a sphere. And then there's this other thing that I'm going to talk a little bit more about tomorrow, which is that, as I told you yesterday, the wave solutions, the wave equations of the supergravity can be reconstructed from the boundary. So you can write the interior in terms of a Green's function integrated over some region of the boundary. And then this HKLL bulk reconstruction methods is exactly about writing clever integral representations of fields in the bulk by doing integrals of various regions of the boundary. Okay? And the point is that they're not unique. There's more than one way to write these things. and they're complicated. Okay. To finish, we know a lot of pieces of the dictionary in the sense that we know all the short words. There's still a lot to learn, so everything about black holes is kind of still to be decided. Black holes and the horizon dynamics are still a mystery. And then tomorrow I'm going to talk a little bit about some other developments that solve other classes of problems and why we might need to rethink a lot of physics in terms of, you know, the modern quantum information theory methods and why that shows up. Okay? Hope this was.
Any questions? So maybe one question. So do you expect that there might be a transition from the giant gravitons, so a smooth transition from giant gravitons to the black hole phase?
Yes. So I've been writing papers exactly on how to do that.
Okay.
So a version of a black hole is take a lot of Dbranes and take a lot of strings stretching between Dbranes and count those. So if you take a lot of giant gravitons and you take a lot of the open strings between them, you can estimate the entropy. And then you can show that these might be dual to a black hole in the sense that there's other ways of counting things that suggest that this is a good way of building black holes. And then when you fix the R charge of the BPS stuff, you can ask, how can I have the maximum number of Dbranes? So the maximum number of Dbranes means each Dbrane has small energy. And the Dbranes with small energy get pushed to the edge. And then what you see is that you get something that has kind of the correct localization on the boundary. And then there's some story there about how to do it properly, but there should be some maximum value of the entropy near this thing, which is roughly where you would expect these boosted black holes to lay. So yes, there's some story there, but it's not.
But that's a free counting of strings on these gravitons that reproduces the black hole.
Well, it doesn't quite reproduce it just yet. It's more along the lines that these are configurations that maximize the entropy given a lot of BPSR charge, and you're just seeing that the happy PS guy, the open strings between them, these small ones are the ones with the minimal energy, and if you try to understand them, the other strings get heavy, so these should be the ones that dominate. So the idea is that the ones that we know are the ones that should dominate, and if you do the counting of that, that more or less reproduces black hole energy, because it's n equal 4 Yang-Mills and finite energy infinite. So there should be something there that's black hole-like. Ballpark, it's more or less okay, but ballpark more or less okay means none of the coefficients of order 1 have been fixed. This is intuition, this is not a calculation.
Okay, that's